This is most of a solution to exercise 4.2.2, a homework problem in week 6 of Math 470. In this problem, we define a function f of x, where f of x equals x cubed if x is a rational number, and f of x equals x squared if x is an irrational number. This function is not close to being continuous. For example, f of 3 is 3 cubed or 27. But f of 3.00100, etc., an irrational number, is just a little bit over 9. So with f of 3 being 27 and f of 3.00100, etc. being 9, it can't possibly be continuous. However, is f of x differentiable at x equals 0? We want to show this using just the definition of a derivative. Let's look at a strategy. These strategies, in general, are not going to be proofs. However, the strategy may suggest to us a method for the proof. So we have f of x. Let's just try to differentiate it. We know we can't do that because f of x is not even continuous. But we won't let that stop us. If we only look at the rational h's and look at the difference quotient for rational h's, we know that the derivative of x cubed is 3x squared. We haven't actually done that in this class, but you should all remember that from the very beginning of Calc 1. If we only look at irrational h's, the derivative of x squared is 2x. And what we notice is that f prime of 0 is 0 for both of those functions. Since both of those are 0, we can guess that the real f is differentiable at 0 and the derivative is 0. Now we're ready to do the actual proof. In this lemma, we need f to be defined on an open interval. It doesn't really matter how large the interval is. We like it to be pretty small. So in this case, let's just take the interval from -1 to 1. Remember that f of x is x cubed for rational x and x squared for irrational x. To prove that f of x is differentiable at 0 and f prime of 0 equals 0, we need to look at the difference quotient, f of h minus f of 0 divided by h. Now this difference quotient is different for rational h and irrational h, because the function f is different. When h is rational, this is h squared. When h is irrational, this is just plain h. I've repeated the formula at the top of this page. Because we're looking at the domain -1 to +1, the absolute value of h is less than 1. That means that the absolute value of h squared is less than the absolute value of h. This gives us a bound on the difference quotient. Absolute value of f of h minus f of 0 over h is less than or equal to the absolute value of h. This bound is true for all h's, rational h's and irrational h's. At this point, the rest of the proof is pretty straightforward. This difference quotient goes to 0, and in fact, if we're given epsilon greater than 0, we can actually choose delta equals epsilon, and that will work. So you need to finish this proof, but the rest of it is pretty straightforward.